Hello everyone, this is discussion 11, question 3, the VM access patterns. Alright, let's look at this virtual memory question. So here we're told that a processor has 16-bit addresses. And remember that the idea with virtual memory is that our programs that are running should kind of think that they have access to the entire address space. And so when we're told that our processor is given 16-bit addresses, that's talking about virtual addresses, right? These are the addresses that are given to us by the program. So these virtual addresses are 16 bits in length. And remember that these are split into an offset and a virtual page number. And so let's continue reading to see what other kind of information we can glean. So we're told that we have 256 byte pages. So remember that our offset is used to index into a page, right? It tells us within one page where is the byte that we're looking for, so the address that we've requested. And so a 256 byte page is 2 to the 8th bytes. And to access anything in 2 to the 8th bytes, I need 8 bits. And so what that means is that my offset needs to be 8 bits. Okay? So this is 8 bits. And since my virtual address as a whole is 16 bits, this means that my VPN has to be 8 bits as well. Okay, now we're told that we have an 8-entry fully associative TLB with LRU replacement. So we kick out the least recently used block here, which is represented by 7, so higher numbers. And the LRU field is 3 bits, right? Because it needs 3 bits to represent 0 through 7. At some time instant, the TLB for the current process is in the initial state given here. Assume that all current page table entries are in the initial TLB. And so what that means is that we don't have to worry about the page table in this case. So with other problems, we're going to be kind of concerned with how the TLB works around the page table. So how to actually deal with page faults and page hits. But here we're only concerned with the TLB. Okay, and then also assume that all pages can be read from and written to. So any of these can have a read or write. And by the way, in case this wasn't clear, this dirty bit here tells us whether that page has been written to. And so if this dirty bit is on, when we kick out that page from the TLB, we need to actually update it in memory. And so it's not as simple as replacing this entry in the TLB. We actually need to update it in memory. Okay. And finally, so fill in the final state of the TLB according to the access pattern below. So I guess let's just start. Remember that each of these accesses are going to be virtual addresses, right? We're assuming that these are things given to us by the program. And remember that our offset is 8 bits and our VPN is 8 bits. So for each of these, we can kind of just split it down the middle. So for the first axis, we're given 0x11F0. So we can split it right here. Our virtual page number is 0x11, and our offset is F0. And so we look for this entry in the TLB. All right, specifically, we're looking for the VPN of 0x11 because our offset, we don't really care about. It just tells us what byte within the page that we want. So we look for this entry in the TLB. We find that it's right here, and it maps to the PPN of 0x14. This is great. Now we can carry out with the, and by the way, we also have to check that the valid bit is on, right? If the valid bit is off, that means that's probably left over from some other process, and it's not a valid mapping anymore. But since our valid bit is on here, this is good. This means that our mapping is valid. Okay, and so after we find out this mapping, we can carry out the rest of our process where we, now that we know that the page we're looking for is page 0x14 in physical memory, we can go fetch that page and look for the offset of F0 and pull in that data. And then going forward with the rest of the memory model, we'd have a cache, right, where we pull in that data into the cache, one block of it, and so forth. But here we're just dealing with the TLB in virtual memory. So what we need to do is update the least recently used bit here in the TLB. And so this used to be fourth least recently used. And so now we have to change this to a 0 and update everything below it, right? So all the entries that were used more recently than it, we change this to a 0 and update all those. So this is going to be a 1. This is going to become a 2. And this is going to become a 3. And this is going to become a 4. Okay. All right, now let's move to our next axis, which is 0x1301. We split it into VPN and offset, and we look for the VPN in the table, and the TLB. So here we're looking for 0x13. We don't find it, and so this means that we need to pull in a page from, well, first we need to go to the page table, but we're assuming that all the pages, or that all the current page table entries are in the initial TLB, so we're actually going to have a page fault here and pull it from disk. But the important thing is that we take our first free physical page, let's say, which is 0x17 in this case, and produce a mapping here. So, and the thing that we kick out is the least recently used entry. And so now we're going to create the entry 0x13 maps to 0x17. So this is the virtual page number. This is the physical page number. And then we'll put it into our TLB, right? And this obviously is the least recently used entry, and we'll kick out the, this is the now most recently used entry, and we'll kick out the least recently used one, which will be this one. Or we could have done this one, but we'll go with the first thing that we see. And so we'll replace that with 0x13, 0x17. Our valid bit we turn on. This is a write, so our dirty bit is going to be 1. And our least recently used, this is now 0. And now we have to increase the least recently used bit for every single other entry in the TLB to keep it consistent. So we'll increase 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and now this is still our least recently used entry. Okay. Now let's move to the next axis. And by the way, I might have forgotten to mention that our first axis was a read, which is why we didn't need to worry about changing the dirty bit here to a 1, right? Because we're just reading from it. So this isn't going to change our data itself, and so we don't need to worry about writing it back to memory when we kick this page out. Okay, now we see the axis 0x20AE. We split it into VPN and offset. So now we're looking for the VPN 0x20 in our table. And we find it right here. And we see that it maps to physical page 0x12. So we need to do a couple things here, right? Number one, this was a write access, and so we need to change the dirty bit to a 1 because we're writing to this. Okay. Number two, we need to change all of our LRU bits. So we saw that this was the 6th least recently used entry, and so we'll change everything below it. We'll change this to a 0, and all of these entries get incremented. So this is going to become a 1. Our 1 is going to become a 2. 2 becomes 3. 3 becomes 4. 4 becomes 5. 5 becomes 6. And this remains at 7. I'll write it out here, just to keep it orderly. Okay. So we found that in our TLB, so we don't need to worry about kicking anything out, but we do need to change the LRU bits. Okay, our next axis is going to be 0x2332. And so we split it into VPN and offset, and now we're looking for this VPN in our page, in our TLB. So we look for 0x23, we don't find it, as this means again that we have to pull it in from the page table, which in this case it won't find in the page table, so it'll page fault and need to pull it from disk. But the important thing is that we need to somehow find a physical page that maps to it and put this into our TLB. So our next, we've already used 0x17, so our next free physical page is 0x18. So we'll create a mapping here from 0x23 to 0x18. This is VPN to PPN. Okay. And we'll put this into our TLB. So to do that, we need to kick out the least recently used thing, which is this invalid mapping here. Okay, so we'll kick that out and put in this entry, which is 0x23 to 0x18. Our valid bit we turn on because this entry is now valid. This was a write access, and so we need to turn on our dirty bit as well. And finally, with our least recently used bits, this is a 0, and we'll increment the rest. So this 0 becomes a 1, this 1 becomes a 2, this 2 becomes a 3, this 3 becomes a 4, the 4 becomes a 5, this is a 6, and this is a 7. Okay. All right, now let's do access 5. So access 5 here is 0x20ff. We split that into VPN and offset, and we check our VPN in the TLB. So we're looking for 0x20. We see that we find it right here. It maps to 0x12, and this is just a read, but our dirty bit is already turned on, so we don't need to do anything here because our page is already dirty anyway, and we already have the kind of the trusted data in our TLB. Okay. So we will change the LRU bits, right? That's the only thing we need to do here. We see that this was a 1, and so we'll change it to a 0 and update everything less than that, which in this case is just this entry here, which was a 0. So we'll change that to a 1. Okay. Last axis is 0x3415. We'll split this into VPN and offset as usual. And now we're looking for 0x34 in our TLB. So we look and we don't find it. And so we need to pull it from our page table and assign a free physical page to it. So our next free physical page is 0x19. So we'll create this mapping 0x34 to 0x19. And this is our VPN to PPN. And finally, we'll put this in our TLB. So in this case, our least recently used thing is actually valid this time, right? It's this row right here. We have a 7. And so we're actually kicking something out that's valid here. And if we access 0xFF again in the future, we need to pull it into our TLB. And so we'll put in 0x34 to 0x19. Our valid bit is 1. Here we're doing a write, so our dirty bit needs to be 1. And our LRU bit should be a 0 here, and we'll increment everything else, right? So this should become a 1, this should become a 2, this should become a 3, this should become a 4, this should become a 5, 6, 7. Okay. And finally, to clean things up, let's rewrite everything here. So our final mappings are 0x01 to 0x11. Okay. Cool. Finally, we'll fill in the valid bits. So we have a 1 for pretty much everything here. Yeah, actually everything. These are all 1s. Our dirty bits are all 1s except for this entry here. So we'll put in all 1s except for 0x11 to 0x14, right? That can we don't when we actually page fault and need to write to disk, we actually won't need to write to disk if we kick out this entry, right? And then these are 1s. Finally, our LRU bits are. This is our least recently used, this entry here, the 7, and this is our most recently used. So this is the thing we'd kick out last, and this is the thing we'd kick out first. Unless we obviously access one of these in between. Then we wouldn't kick this one out last. Okay, so that is question 3, VM access patterns.